In this video, we're going to be looking at example 4 from our optimization notes. So just as a refresher, make sure that you're looking at these steps as you're practicing these optimization problems to make sure you hit all these steps before you box your answer and move on to the next one that we went over in class. All right, so we're going to pick up at example 4. Lost control. Where we've got a rectangle inscribed inside of a semicircle bordered by the x-axis. A semicircle equation is given to us. We're asked to find the dimensions of the rectangle that would maximize the area of the rectangle. So far, we have we've read our problem and understood it. We've stated what we're asked to find and given ourselves a space to write our final answer. We've labeled our diagram that they gave us with, most importantly, the points on the vertices. That's what I was working. The points on the vertices where the upper corners of the rectangle hit the semicircle, because those are going to be points along that semicircle. So they're going to have an x value of x and a y value of whatever the square root of 25 minus x squared is. That'll give us our dimensions. So our height is going to be that y value. Our width is going to be twice that x value since we're symmetric about the y-axis. Excuse me. So that gives us the length and width of our rectangle in terms of x. So then those are our secondary equations. So we substitute those into our optimization equation, which we're asked to maximize area. So that's length times width. So plugging those in, we got our formula for area. So we need to then take our derivative in order to find our critical points, in order to find our extrema. So we did our product rule, and we found our derivative to be this sum of these two terms that both have square roots in them. So to find our critical points, we need to take our derivative and set it equal to 0 and set it undefined. So we've got setting it equal to, well, let's do undefined first. So we've already set the denominator equal to 0 and found that x could be positive or negative 5 in order to make that denominator 0. Our constraints for our problem were x is bounded between negative 5 and 5. So since those two endpoints aren't included, that didn't give us anything extra. What we also should do, this isn't going to actually help us get to our final answer, but what we should do, since this is a square root, we also need to consider that whatever's under the square root, 25 minus x squared, that can't be negative either, okay? Because that'll make the square root undefined, which will make the whole derivative undefined. Okay, so if we solve this out, if we do our difference of squares, or you can add x squared to both sides. Either way. Then we're going to get 5 minus x less than 0 and 5 plus x less than 0, which if we add x to both sides, and if we subtract 5 from both sides, then we're going to get that our x value, in order to make it undefined, if our x value is bigger than 5 or less than negative 5, our derivative would also be undefined, which makes sense. If we look back at our graph, the original function itself isn't defined for those values, so it makes sense that the derivative is not defined. If any of these values were in our range, we would want to take that into account. They're not, so that doesn't add anything to our final answer. So let's go over to our a prime equal to 0. And this is where our calculator comes in handy, to where we can find any time where we have zeros on our derivative. So let's go to our calculator. I've already got our equation in here into y1. Be careful about functions like this that have multiple parts. Make sure that you are telling your calculator exactly what you want to graph. All right, so I've got it in. I'm double checking to make sure it matches what I want. And then for our window, I'm just going 0 to 5. So you could go -5 to 5, but any x values that are positive are going to give us the same rectangle for a negative x value, since it's an even function. It's symmetric about the y-axis. So I'm just going 0 to 5. Y min and max don't matter as long as you go from negative to positive, so we can see that x-axis. So when we graph it, we see 1, 0 here. So again, don't just use trace and approximate it. We have our calculators to get an answer accurate to the nearest thousandths. So let's use second calc. Find our 0. We want a left bound. We want a right bound. Again, this just tells the calculator, hey, look between these 2 points for a 0. And guess. And we get x equals 3.536. X equals 3.536. All right, as our only critical point. All right, and we could see on our derivative graph that it went from positive to negative. All right, it had that negative slope there. So that tells us on our original function changes from increasing to decreasing, which again verifies that it is a max and not a minimum. Okay, so we want to say max at x equals 3.536. Since f prime, or in this case a prime, changes sign from positive to negative. All right, so we verified that extrema is a max, and so that's what we're looking for. We're looking for the dimensions that will maximize the area. That's not what we're looking for, Mr. Flory. We're looking for the dimensions. So how does that fit into our dimensions? If we go back to our definitions for length and width, then we need to plug that back in to these two here. So we needed to double that. So I'm going to go back to my calculator, and when we find the 0, your calculator stores that value into x. So if we just go back to our home screen and press 2x, boom, there's our width of our rectangle, so 7.071. All right, and our height is going to be whatever we get when we plug into that. So let's go square root 25 minus, and again, I can use x here because that x value is stored in there, because I found the 0 on the graph there. Otherwise, I'd have to retype it in. All right, we get 3.536. Isn't that same as our input? Same as our input. All right, and that's our length, okay, or height. Okay, and we don't need to worry about units. We're on the coordinate plane. So dimensions that'll maximize our area are 7.071 and 3.536.